All right. Okay. So thank you so much for coming to our talk on PipelineRL, RL training speed through the roofline. This was work done at ServiceNow with Isan, Rafa, Xiaoyan, and Dima. Okay. So if you've been training LLM with RL the last few months, like the odds are you've been doing some reasoning, trying to teach LLM to reason from scratch, right? So your workflow probably looks something like this. You have a data set of prompts, like math questions, and maybe you're using your full node, like using 8 GPUs to serve like 7B model. And you're going to query them. You're going to ask them like, oh, generate completion, tell me how to solve this math problem. And some of those answers are very long. Some of them are very short. Some of them are like, oh, wait, let me think about this, blah, blah, blah. Right? Then you're going to take the answer, you're going to parse them, you're going to give them rewards. 1 if you solve the answer, 0 otherwise. Then you're going to take all those prompt completion and rewards and you're going to train on it. Probably so with some kind of distributed system like DeepSpeed, TorchTitan, or the like. And then you're going to update the inference weights. And here you have two like you have like all the training and all the inference that usually use all the GPUs at once, right? So it's a very sequential process. First the prompt, then the training, first the generation, sorry, and then the training. And we call this a RL step, right? How many optimizer step you do per RL step? This is 1 RL step. Okay, so in this talk, we're going to discuss how to speed up R training by getting the most out of your inference GPUs. This is all what PipelineRL is all about, getting those GPUs working for you and like getting RL very quickly to learn. Okay, so here we're going to look at the roofline of the inference engine. And roofline is just like some visual model of performance to understand if you're memory or compute bound. And it's also the pun in the title. So here on the y-axis, we have performance flops per second. And we have the maximum potential flops per second of NVIDIA H100 or A100 that's possible at the in. And on the x-axis, we have arithmetic intensity. So that means how much compute can you do per byte in the compute unit, right? So for this talk, I'm just going to refer to it as batch size, since we're just simplify for inference. And for very small batch size, you're memory bound. Why is that? So imagine you have this big model, like 70 billion parameter, whatever, and you just want to have batch 1. So what you're going to do, you're going to take the weights and you're going to stream them to the compute engine, and you're just going to do a little bit of flops, right? And you're like, oh, this is so wasteful. I bring a lot of data in and out, and I don't do much computation. As you increase the batch size, like you still have to bring the data in and out anyway, but you can do more operation. And then as you increase the batch size, you're going to be compute bound, and you can achieve higher flops, right? And empirically, we tested this and on a Qwen 7B, on a single H100, when we start at 4 batch size of size 4, we're memory bound as expected, and we don't produce much tokens per second. But as we increase the batch size to, in this case, 256, we can get 7,000 per second. Right? Okay, so now we found a batch size we like that get a lot of tokens per second. We're very happy. But if we're not careful, so example, here we have 4 sequences. So we have the prompt, and each of those prompts are starting to complete, right? But some of them are going to finish much earlier than others. So now your GPUs are idle all the time, right? You can see I started at 4 batch size 4, and then batch size 2, and then just batch size 1. So the GPU goes back into being memory bound. Okay. So instead, everyone's doing is our continuous batching. So when a sequence ends, you add another one, and now you can run at constant batch size 4 in this case. Okay. So this was kind of a mini intro to inference engine. Now let's look how this works with conventional RL. Right. So this is a very didactic example. We have 8 GPUs, and each of them have a batch size of 1. So conventional RL take all the GPUs, start to generate, right? And as expected, some of GPUs are idle as soon as like the sequence ends. And then you take all your completion when they're done, and you start optimizing. You do 1 optimizer step. And this is what we refer to, again, to a RL step. You get enough data for 1 optimizer step, you do your optimizer step. And here, note that after the optimizer step, the color change, right? Here, the color refer to the weight version. So we collected the data under the light blue weight. We did the optimizer step under the light blue weight, so we're very happy on policy. But then the color change, and we have a new policy. Okay. So you would tell me, just generate more rollouts, right? Instead of generating 8, generate 16. So this is what we can do here. Twice the number of rollout, twice the number of steps. That's great because now, like proportionally, we have less GPU idle time. So we're happy. But now we have a lag, right? Like the data was collected under the light blue policy. But after one optimizer step, the policy changed, here represented by a darker shade of blue. And now we have a lag in between. Okay. And indeed, when we increase the number of rollouts we process, we can get them like it's much faster. So this was also done on a single H100 with Quan 7B. We can get 128 rollouts in roughly 120 seconds, right? But you can see there's a very low inference batch size when those the shorter sequences are being completed. But if you do 1,000 rollout, 1,024, you can do it in 420 seconds. So 8 times the number of rollout and 3.5 times the time. So there's some kind of trade-off, right? You have on the rightmost, like throughput, how much sample can you get per second? So you want this to be high, but you have effectiveness, like kind of this ideas of off policy, like sample that are off policy are a bit less valuable than the on policy one. And what you would want is like, you want to maximize both. You want good throughput, but you want good samples. And that's going to give you good speed. So here the speed is like the amount of reward you can improve your policy by an amount of time, right? Effectiveness is how much reward you can get per amount of samples. And throughput is, of course, number of samples you can get in the amount of time. Okay. So here, for very on policy, G1, we have very low GPU utilization. So we're kind of the extreme where we have very good learning effectiveness. The sample are very good, they're on policy, but we're not too good in sample generation and throughput, right? As we increase G at the other end, we have good GPU utilization, but we become very off policy. Okay. All right. So now let's talk about PipelineRL. How do we handle this trade-off? Okay. First thing, PipelineRL compared to conventional RL, there's multiple processes running in parallel, right? The first one is generating data. So we have the actor process, whose job is to keep the inference LLM busy. So to keep them running at like the target batch size, in this case, the 2 LLM, and it's going to stream the data, in our case, through Redis, right? And here, like they're going to have rewards too. Then we pass to the preprocessor. Preprocessor, that's where you do, if you want to annotate your rollouts, where like the base model probability in very light blue. You do sequence packing, sequence parallelism. It happens all in the preprocess, which dump the data to the trainer in the last processes. And now here, like deep speed in our case, update the weights and ship back the weight to the inference engine. Okay, so let's take a look what it looks like in our didactic example. So we have our half our GPUs in our case used for generation and half for training. And again, here the weights are changing with the colors, right? So PipelineRL run with constant batch size. So you wait for the sequences to be done. When you have enough sequences, you take an optimizer step. And as soon as the optimizer step is done, you do an in-flight weight update, right? So what does that mean? If we zoom in, like between 2 tokens, we updated the weights. So the sequence started under the light blue policy, but it terminated under the darker blue policy. So the previous tokens that we generated at the beginning of the sequence are now off policy, while the new tokens are on policy. So it's a bit different from PipelineRL, right? From a conventional RL, where samples were sampled under a policy. It's kind of a mixed policy. Okay. So what does it mean? It means like after the in-flight weight update, some sample, like the future optimizer step, are somewhat off policy, or some tokens are not collected under the current policy. Okay. So now I'm going to give you a small demo, what it looks like from learning from scratch. Okay. So in our case, we wanted to replicate the open reasoner 0. So they use Quen 2.5 base 7. They have their own data set. We use 16 nodes, and our completion are up to 32,000 tokens. Okay. So now I replay the logs to see like the speed of the difference between conventional RL with G32. G32 here being you collect 32 batches during a RL step, and then you do 32 optimizer step. The G32 is the largest G we can get without starting to diverge. We try G64 next. So G32 is the highest. Like all the x-axis are time, so how much seconds since the beginning. And the first figure is going to be the inference batch size. Like what's the average batch size running on every one of our GPUs? Okay. Then the second chart is how much samples are getting through the whole system. And finally, it's going to be reward over time. Okay, so let's start playing this video. Okay, so let me start it immediately here. So we can see in the red conventional RL, start at batch size 256, but decrease quite quickly, right? Because like shorter sequences are done, and we have a lot of GPUs in this case. So like the batch size per GPU becomes very low, while PipelineRL keeps the batch size constant. And since PipelineRL also start training on sample as soon as they're ready, you can see the system samples starting to go up. It's already at 100,000, and it made like 100 optimizer step already, and like the rewards start going up. And conventional RL still waiting for the last sample to arrive. So you can see now, like the same thing happen over and over again for every RL step, conventional RL up and down. And here I let it run for 8,000 seconds. You can see the sample that went through PipelineRL is like 3 times the amount. Learned much faster, and now conventional RL was starting to catch up. So conventional RL, like very good algorithm, it's going to be able to achieve good performance, but it's much slower. Oops. Okay, so now we're going to look at more detailed results. So the first thing I'm going to show you is we're going to vary conventional RL from 8 optimizer step to 32. So 8 optimizer step mean you collect 8 batches per RL step, and G32 is you collect 32. So you collect much more sample. And as expected, in this case, we want to collect 1,000,000 something samples. As you increase G, you're much faster, right? But PipelineRL stay even more faster. In this case, it's roughly 2x sample faster. So you can collect and train on 1,000,000 sample in roughly 75 minutes, while G32 here can do it in, let's call it 140, 145. Okay, so here, the number of sample per minute. Now, if we just look at the reward per sample, those are all roughly the same algorithm. They all like importance weighted reinforce. So there's not much difference. Like I would be hard pressed to tell you which one between G8, G16, and PipelineRL, which is which. But you can see G32 being maybe a bit slower and a bit more unstable, right? Because this is like one near the limit of policy you can get. And putting everything together, since we have like the same sample efficiency in terms of reward per sample, but we're faster to collect the data, PipelineRL achieve the same reward in half the time. Okay. And we wanted to compare, can we match the result from opener reasoner 0, right? Just to know, like, can we trust our implementation? So open reasoner 0 roughly has 82 on Math 500 and 20 on AMI 24. And we obtained something very similar where we have 84.6 on Math and 20 also on AMI 24. So Dima is going to come and uncover the in-flight wait update.
You're going too fast. Going too fast. Somebody in my slide. Okay, so that that was the end of the useful part of the talk. Now there will be the theoretical part of the talk. So what makes PipelineRL special are in-flight wait updates. To explain what in-flight wait updates are, I will first talk a little bit about how inference works. Many of you know it, but maybe some of you would like a little recap. That when a prompt arrives to the transformer, when a prompt arrives to the inference engine, first you have to process it, and the result of processing is basically key value cache. Then you compute the likelihood of the next token, then you generate that next token, and you remember the keys and values for that token, so they become a part of the KV cache. And this process goes on again and again. Prefill, generation, another generation. So how can you update the weights in the process without stopping this process in this case? What happens when we do in-flight wait updates is that we just continue from the old KV cache. So here you can see the weights have changed, but we don't touch the KV cache. It's there, it's in the memory of the inference engine, and we use the old values of KV, old keys and values of KV cache that are still there in memory. Another wait update comes, and we continue generation from a sequence of mixed keys and values that come from various, from a number of subsequent generations of the model, versions of the model. So, many people, I actually had an interesting conversation with VLM developers recently in Slack. They told me they were really surprised this works. They were like, "What are you doing? This is crazy. It's these KV values are wrong. Like, how can you continue generating from them?" So we decided that in order to convince everyone that that is okay, that using stale KV cache is okay, we did some study where we looked at actually the difference between the log likelihoods, between the logits that the current model produces and the model that's currently trained, and the logits produced by the behavior policy. So we call this behavior policy that is using mixed different versions of weights different times. We called it mixed behavior policy. So on this slide, the x-axis is the lag between the behavior policy and the current policy, which is what is the maximum number of weight updates that happened between so you take the token that is generated by as old as possible version of the model, and you take that version of the model, and you take the current version of the model, you look at the difference. So that measure of staleness, we call it the lag. And what we see is that for the same value of lag, the difference between the behavior policy and the current policy is actually way lower for PipelineRL. And what's very interesting, even if we recomputed KV cache, which is extra computation, it would be, the KL would remain the same. So at least with the learning rate that people usually use for reinforcement learning, which is typically a very small learning rate around 10 power minus 6, at this learning rate, what we can see here is that KV cache staleness is not a problem at all, and we can see that PipelineRL stays way more on policy than conventional RL does. The reason, I mean, there is a bit, we're kind of beating a straw man here because we use a very long sequence length, in which case, which is a setting that is beneficial for PipelineRL, and you'll see why in this slide. So I think here I would like to show you that the structure of policiness is different for the conventional RL and the PipelineRL. So for the conventional RL, if you do, let's say, 3 optimizer steps between two model updates. The first optimizer step is done using purely on policy data. Second, you have a data with leg 1. Then you have data with leg 2, and so on. It's much more interesting in PipelineRL. So every sequence consists of tokens with different value of lag. All the latest tokens that were generated recently, the tokens at the end of each sequence, they have a smaller lag. They have lag 0. And tokens closer to the beginning of each sequence, they're going to have a higher value of lag. So if your optimizer step consists of sequences with very different lengths, the majority of tokens will be at the end of those sequences. So for the majority of tokens will actually have a low lag. You will never have a batch that has all tokens with very high lag that were produced by a very old version of the model that doesn't matter anymore. So that is why in the previous plot, you see the difference between the behavior policy and the current policy is way smaller for PipelineRL. Something interesting happens when you double the amount of compute that you're using for PipelineRL. If you have 2x GPUs for inference and 2x GPUs for training, each training step takes twice as little time as before, while inference, the latency of inference hasn't changed. And effectively, this doubles the lag for PipelineRL. So, yeah, high lag. Alex made the slides. We have high lag tokens in the beginning of the sequence. We have low lag tokens in the end of the sequence. So I think that this plot is a little bit abstract, but it's the best summary of our project. It shows that PipelineRL is an alternative reinforcement learning method where you trade effectiveness for throughput by changing the amount of compute that you use for training. So the more compute you throw at your problem, the higher the throughput is going to be, but at some point, the learning effectiveness of that throughput is going to be low because you will be way too much on policy. This trade-off is akin to the trade-off that you have in the usual reinforcement learning, where the parameter is the number of optimizer steps you do in between the weight updates. The same thing with that parameter. The more you crank it up, the higher the throughput is, but the learning effectiveness goes down. So what we claim is that PipelineRL takes you to a better ISR curve. So it has a better Pareto frontier between effectiveness and throughput. And PipelineRL, I mean, it's basically asynchronous RL. So any properly implemented asynchronous RL will have the same pictures here. PipelineRL is just a very radical version of asynchronous RL where we don't stop anything ever at all. We don't stop the inference ever. Yes, so less accelerators. With less GPUs, you're more on policy. With more GPUs, you're less on policy. Oh, that's already Alex's section again.
All right. Okay, so let's say you're convinced and you want to use PipelineRL now. How hard is it going to be? It's not going to be that hard. Like you have two main functions that you need to implement. The first one is a kind of a load data set. So in this case, like the example I'm showing you is a guessing game where the agent has to guess an int and the user is kind of telling it higher or lower. So it's just a simple data set loader that basically split the int into train and test. That's very easy to do. And then we have an async generate function, which is also fairly simple. So what it looks like is, in this case, we're going to generate up to 13 turns, like it's multi-turn, like the agent, oh, is it 512, higher or lower, and then so on and so forth. And you just collect the LLM calls, right? Like our LLM engine generate completion, generate tokens, give you log probs. You just store all of this. and you compute what your reward is going to be. And then you're going to create training text. Training text is everything you need to do to make RL. So like the probability under your current policy, the reward is going to be there, so on and so forth. And you're going to return what we call a rollout result. And PipelineRL is going to take care of everything else. It's going to normalize, it's going to do GRPO or PPO, whatever you want. So it's very simple getting started. Okay. So in conclusion, why PipelineRL? We effectively use Inference GPUs, right? Like it's very fast. It's up to 2x faster. We have reinforced PPO with the value function if you want to play with it. GRPO. It's a very research-focused code base. Like it's very easy to expand if you want to add new things. My intern keep adding new features and is able to get a lot of work done. So it won't get in the way. I wouldn't say it's tested at massive scale, but we scale it up to 16 nodes and it's been stable. We have multimodal support. We replicated the work of Armin Mastery, like chart QA, where we're able to train an agent via GRPO to answer questions about charts. We have sequence packing and sequence parallelism, so you can train to like 128,000 token sequences. And as you saw, we have some kind of multi-turn agenting training. It works very well. And we're going to have one where the agent called MCP tools was able to reason about math and call the Python interpreter to help itself. Should be merged in main soon. So thank you all for joining us. And if you want to go to the GitHub or the archive, please do. And yeah, I think we're going to take questions now.